Hello everyone. Today we will study Poisson distribution. First of all, let me introduce what it is. For Poisson distribution, in order to introduce what it is, let's first of all assume the following conditions. So for Poisson distribution, we need to assume the following conditions. First of all, we assume events occur continuously. First of all, we assume events occur continuously. And the occurrence of the events are independent. Occurrence of the events are independent. Also, in any time intervals with the same length, of the same length, or any place with the same area, the average number of the occurrence of the event is the same. The average number of an occurrence of the events is always the same. So for Poisson distribution, we must make the following assumption. Events occurs continuously, and occurrence of the events are independent. Also, in any time intervals of the same length, or any place with the same area, the average number of the occurrence of the events is always the same. Now, let's consider this. In a fixed time interval, let's consider this. In a fixed time interval, or a place with fixed area, suppose lambda is the average number of occurrence of the events. Suppose lambda is the average number of occurrence of the events. Let the random variable x then the random variable x represent the actual number of occurrence of events. Let the random variable x represent the actual number of occurrence of the events. Then we say x has a Poisson distribution with parameter lambda. Let x represent the actual number of occurrence of events. Then we say x has a Poisson distribution with parameter lambda. Next, we try to find its probability function. Next we try to find probability function f of x. Think of this. If we divide the time interval or the place into n equal subintervals, or subregions. If we divide the time interval or the place into n equal subintervals or subregions, then the probability that the event occurs in the region in the subinterval on each subinterval is what? If we divide the time interval or the place into n equal subintervals or n equal subregions, then the probability that the event occurs on each subinterval is what? How do we find the probability here? How do we find the probability that the event occurs on each subinterval? Let's look at some simple examples first. Let me show you some examples. First example, when fishing in a lake, we catch fishes at an average rate of 2 fishes per hour. then we know that in a 1 hour time period, which is a fixed time interval, in a 1 hour time period, which is a fixed time interval, lambda is 2. And the average number of occurrence of an event is 2. Now, if we divide the time interval into 6 subintervals, into 6 equal subintervals, which means n equal to 6. We divide the time period into 6 equal subintervals, which means n equal to 6. What's the probability of catching a fish in each subinterval? What's the probability of catching a fish? In each subintervals? Let's think of this. In a 1 hour time period, from 0 to 60, 0 minute to 60 minutes, in a 1 hour time period, we are able to catch fish at an average rate of 2 fishes per hour, lambda equal to 2. We are able to catch fish at an average rate of 2 fishes per hour, 2 fishes per hour. If I divide this time interval into 6 equal subintervals, then I have 0 to 10 minutes, that's the first interval. 10 to 20, that's the second one. 20 to 30, 30 to 40, 40 to 50, 50 to 60. If I divide the time interval into 6 equal subintervals, what's the probability of catching a fish on each interval? We know that in 60 minutes, we're able to catch 2 fishes. If I divide 2 fishes into 6, I get 1/3. That means on each interval, we are able to catch 1/3 of the fish. If I take 2 divided by 6, that means on each subinterval, we're able to catch 1/3 of a fish. If I take lambda divided by n, I get 1/3. If I take lambda divided by n, I get 1/3. That means on each subinterval, we're able to catch 1/3 of a fish. Lambda over n equal to 1/3. That means on average, we can catch 1/3 of a fish on each subinterval. So we can catch 1/3 of a fish on each subinterval. If we can catch 1/3 of a fish on each subinterval, it also means the chance of getting a fish on each interval is 1/3. it also means the probability of catching a fish on each subinterval is 1/3. If we're able to catch 1/3 of a fish on each interval on average, that means the chance of catching a fish on each subinterval is 1/3. And this probability is the same on every subintervals. This probability is the same on each subintervals. If we let a random variable x represent the number of caught fishes in a 1 hour time period, then x is what? Then x is very, very close to a binomial random variable. Binomial random variable with n equal to 6 and p equal to 1/3. The probability of getting success is 1/3 on each interval here. The probability of getting a fish is 1/3 on each time interval here. And there are 6 time intervals. So x is very, very close to a binomial random variable with n equal to 6 and p equal to 1/3. But why we say x is very close to a binomial random variable? Is x a binomial random variable? Why we say it's very, very close to a binomial random variable? The probability of getting a fish is 1/3 on each time interval. And there are 6 intervals here. Why we say x is very, very close to a binomial random variable? Keep this question in mind. I'll go back to it later. Keep this question in mind. I'll go back to it later. Why we say x is very close to a binomial random variable? Why we don't say x is a binomial random variable? Why we say it's very close? Keep this idea in mind. Keep this question in mind. I'll go back to it later. Let's look at another example. Example 2. Every morning, in the surface of a lake, we find 3 garbages on average. Then we know that on the surface of the lake, every morning on the surface of the lake, on average, we expect to get 3 garbages. On average, we expect to find 3 garbages. That means lambda equal to 3. Every morning on the surface of the lake, we expect to find 3 garbages. That means lambda equals 3. Now, if we divide the surface of the lake into 12 equal subregions, if we divide the surface of the lake into 12 equal subregions, what is the probability of finding a garbage on each subregion? What's the probability of finding a garbage? On each subregion. Consider the surface of the lake. Suppose that's the surface of the lake. On average, we expect to find 3 garbages on the surface of the lake every morning. On average, we expect to find 3 garbages on the surface of the lake. So lambda is 3. On average, we expect the event occurs 3 times. On average, the event occurs 3 times. Lambda is 3. If I divide the surface of the lake into 12 equal subregions, then on average, we expect to find, we take lambda over n, 3 over 12, that's 1 over 4. Then, on average, we expect to find a quarter of a garbage on each subregion. On average, we expect to find a quarter of a garbage on each subregions. On average, we expect to find a quarter of a garbage on each subregion. That means the probability of finding a garbage on each subregion is 1 over 4. That means, on average, the probability of finding a garbage on each subregion is 1 over 4. So here, lambda over n is 3 over 12, which is 1 over 4. That means on average, we can find a quarter of a garbage on each subregion. On average, we can find a quarter of a garbage on each subregion. If we can find a quarter of garbage on each subregion, that means the chance of finding a garbage is 1 over 4 on each subregion. it also means the probability of finding a garbage on each subregion is 1 over 4. The probability of finding a garbage on each subregion is 1 over 4. And the probability, this probability is the same for every subregion. This probability is the same for every subregion here. And this probability is the same for every subregion. Here, if I let the random variable x represent the number of garbage found on the surface of the lake, if I let the random variable x represent the number of garbages found on the surface of the lake in the morning, then since the chance of finding a garbage is 1 over 4, and the chance is the same for every subregion, then we can say x is very close to a binomial random variable. Then we say x is very close to a binomial random variable. With n equal to 12, because there are 12 different regions. And p equal to 1 over 4, because the chance of finding a garbage is the same for every subregion. But why we say x is very close to a binomial random variable? Why we don't say x is a binomial random variable? Let me give you a little review about binomial distribution, then you'll see why. For binomial distribution, think of a set S. S contains only two elements, success and failure. For every trial, the chance of getting success is P. For every trial, the chance of getting success is P. And we repeat the experiment n times. We repeat the experiment n times. N is the number of total trials. The total number of trials. If I let x represent the number of obtained success, then x is a binomial random variable. If I let x represent the number of obtained success, then x is a binomial random variable. So for binomial random variable, you can see that for every trial, the chance of getting success is the same. And also, for every trial, we are either getting no success or one success. We won't get more than one success. We won't get 2 or 3 success. For every trial, we are getting either no success, 0 success, or 1 success. We won't get more than 1 success. In a binomial distribution, experiment, for every trial, we are getting either 0 success or 1 success. We won't get more than 1 success. We won't get 2 or 3 success. For every trial, we are either getting 0 success or 1 success. If I pick failure, I get 0 success. If I pick success, I get 1 success. I won't get more than 1 success. And we won't get more than 1 success. So keep this idea in mind. For every trial, for every binomial trial, for every Bernoulli trial, we are either getting 0 success or 1 success. We won't get more than 1 success. But let's go back to these 2 experiments here. In these 2 examples here. In example 2, lambda is 3, means on average we have 3 garbage on the surface of the lake. It's possible that we have 2 garbages in the same region, in the same subregion here. It's possible that we have 2 garbages on the same region. So in this case, for this trial here, we are getting 2 success. It's possible that there are 2 garbages on the same region. In this case, we are getting 2 success in this trial. For this trial here, we're getting 2 success. That's why we say x is very close to a binomial random variable. X is not exactly a binomial random variable. It's possible that we are getting 2 success in 1 trial. Same thing in the first example. It's possible that we are catching 2 fishes in this time interval. It's possible that we are catching 2 fishes in this time interval. That means for this trial here, we are getting 2 success. That means for this trial here, we are getting 2 success. That's why we say this x is not exactly a binomial distribution. It's very, very close to a binomial distribution. Now, how do we make x to be a binomial distribution? How do we fix the problem and make X to be a binomial distribution. Think of this. If we can make the subintervals smaller, when the subintervals are sufficiently small, then on each subinterval, it won't have more than one success. If we can make the subintervals sufficiently small, then on each subinterval, it won't have more than one success. Then, since the chance of getting success on each subinterval is the same, and we won't get more than one success for each trial, then X will be a binomial random variable. But how do we make the subinterval sufficiently small? Think of this. As n approaches to infinity, if we make n very, very big, then each subinterval will be very, very small. Then each subinterval will be very, very small, which means it won't have more than one success on each subinterval. Then it won't have more than one success on each subinterval. That means for every trial, we are either getting 0 success or 1 success. We won't get more than 1 success. Then X will be a binomial random variable. So X will be a binomial random variable. Same thing for this example here. If we make n sufficiently large, each subregion will be sufficiently small. If we make the subregion sufficiently small, then on each subregion, it won't have more than 1 success. Then, since for every trial, the chance of getting success is the same, and we won't get more than 1 success for each trial, then X has a binomial random variable. X will be a binomial random variable. Now, let's go back to our original question. In a fixed time interval, suppose lambda is the average number of the occurrence of the events. If we divide the time interval into n equal subintervals, then the probability that the event occurs on each subinterval is what? Look at these two examples. In the first example, the probability that the event occurs on each subinterval is 1/3. How do we get 1/3? We use lambda over n. In the second example, the probability that the event occurs on each subregion is 1/4. How do we get 1/4? We use lambda over n to get 1/4. So similarly, the probability that event occurs on each subinterval, we can also use lambda over n. The probability that event occurs on each subinterval is lambda over n. And this probability is the same for every subregion. This probability is the same on every subinterval. Now think of this. As n approaches to infinity, each subinterval will be sufficiently small. That means on each subinterval, it won't have more than 1 success. Then for every trial, we are either getting 0 success or 1 success. Then X will have a binomial distribution. So as n approaches to infinity, X tends to a binomial distribution. x tends to a binomial random variable. As n approaches to infinity, x tends to a binomial random variable with parameters n and p. And this n is the same as this n. P is what? The chance of getting success for each trial is lambda over n. The chance of getting success for each trial is lambda over n. The event occurs on each subinterval is lambda over n. That's the chance of getting success for each trial. So, since x is a binomial random variable as n approaches infinity, then f of x is what? If we use binomial distribution, the formula is, the probability function for binomial distribution is n choose x times p to the power of x times 1 minus p to the power of n minus x. And we take a limit. Here we must take a limit as n approaches to infinity. Since x is a binomial random variable, its probability function is f of x equal to n choose x times p to the power of x times 1 minus p to the power of m minus x. So f of x can be rewritten as limit n approaches to infinity n choose x times p to the power of x. Here p is lambda over n to the power of x times 1 minus p. P is lambda over n to the power of m minus x. Now, let's simplify this. Get a probability function of x. Let's simplify this. Get a probability function of x. N choose x can be rewritten as n factorial over m minus x factorial times s factorial. Lambda over n to the power of x can be rewritten as lambda to the power of x over n to the power of x times 1 minus lambda over n to the power of n minus x. That can be rewritten as 1 minus lambda over n to the power of n times 1 minus lambda over n to the power of negative x. Now let's simplify this. This limit is about n, so I can treat everything else as constant. This limit is about n. I can treat everything else as a constant. So I can pull out s factorial. I can pull out lambda to the power of x. These two expressions doesn't contain n. I can pull it outside the limit. So I can pull out lambda to the power of x. I can pull out x to the power x factorial. These two expressions doesn't contain anything about n, so I can treat them as constant. Pull these two terms outside. What's left is n factorial over m minus x factorial. Since I pull out s factorial, I have n to the power x on the bottom times 1 minus lambda over n to the power of n. I separate this into two terms, power n, power of minus x, times 1 minus lambda over n to the power of negative x. Then This limit can be rewritten as limit n approaches infinity n factorial over m minus x factorial times n to the power of x times limit n approaches infinity. I take limit for each part, for each term individually. Take limit for each term individually. Limit 1 minus lambda over n to the power of n times limit as n approaches infinity 1 minus lambda over n to the power of negative x take limit for each part individually. Let's take limit for the first part first. Let's take the first limit first. Limit n approaches to infinity n factorial over m minus x factorial times n to the power of x. How do we take limit for this? On the numerator, we have n factorial. N factorial is n times n minus 1, n minus 2, Eventually, it will reach m minus x. So eventually it reach m minus x plus 1, m minus x minus 1, m minus x m minus x minus 1, 3 to 1, eventually reach 1. On the bottom, we have m minus x factorial. Let me put it on the back. M minus x factorial is m minus x minus 1, eventually it will reach 3 to 1. Now, how many terms do we have here? How many terms do we have here? From n to m minus x plus 1, how many terms do we have here? Think of this. From 20, 19, 18 to 11 and 10, how many terms do we have here? Let's count. 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, and 10. There are 11 terms. How do we get 11? A quicker rule is you can think of 20 minus 10 plus 1. 20 minus 10 plus 1, there are 11 terms. Another example, from 35, 34 to 20, 21, 20. How many terms do we have here? We can count, right? 35, 34, 33, 32, 31, 30, 29, 28, 27, 26, 25, 24, 23, 22, 21, 20. There are 16 terms. How do we get 16? We can think of 35 minus 20 plus 1. That's 16. Similarly, how many terms do we have here? From n to m minus x plus 1. From n to m minus x plus 1, how many terms do we have? Similarly, we can use the first term minus the last term plus 1. So use the first term minus the last term plus 1. What do we get? M minus x we have n minus n plus x minus 1 plus 1. Cancel n, cancel 1, we have x. So from n to m minus x plus 1, there are x terms here. there are x terms. And on the bottom, n raised to power x. On the bottom, n raised to power x, there are also x terms. We have n, there are x n's here. So we have the same amount of terms on the top and the bottom. We have the same amount of terms on the top and the bottom. Next, on the top and the bottom, I can cancel m minus x minus 1, everything until 3 to 1. What's left here is limit n approaches to infinity n over n times m minus 1 over n times m minus 2 over n times m minus x plus 1 over n. The rest get cancelled. Now, if I take a limit as n goes to infinity, this is 1. This limit, if I use L'Hopital's rule, this is also 1. This limit, if I use L'Hopital's rule, this is also 1. For this limit, since I treat s as constant, as n goes to infinity, I use L'Hopital's rule. It's also 1. So 1 times 1 times 1 times 1. Altogether is 1. So the first limit, n factorial over s minus n factorial times n to the power of x equal to 1. The first limit equal to 1. Next, let's take the second limit. Take limit as n approaches to infinity. 1 minus lambda over n to the power of n. What do we get for this limit? If I plug infinity, lambda over infinity is 0. 1 minus 0 is 1. If I plug infinity here, I get 1 raised to infinity. 1 to the power of infinity is not 1. This is indeterminate. This is an indeterminate form. 1 to the power of infinity is not 1. This is an indeterminate form. So here, in order to take a limit, think of this way. Let y equal to 1 minus lambda over n to the power of n. Let y equal to 1 minus lambda over n to the power of n. Then apply ln on both sides. I get ln of y equal to ln of 1 minus lambda over n to the power n. Then on the right side, I can bring n to the front. Next, I can bring this n to the bottom. Write it as n raised to negative 1. I can bring this n to the bottom, make it as n raised to negative 1. Next, I take a limit. Take a limit as n approaches to infinity. Take a limit on both sides. N raised to negative 1 can be written as 1 over n. Then as n approaches to infinity, what do we get here? On the top, lambda over infinity is 0. 1 minus 0 is 1. Ln of 1 is 0. On the bottom, 1 over infinity is also 0. So we get 0 over 0. When we get 0 over 0, we can apply L'Hopital's rule. If I apply L'Hopital's rule here, what do we get? If I apply L'Hopital's rule here, I take derivative from the top and the bottom individually. For the numerator, if I take derivative, I get 1 over 1 minus lambda over n times the derivative from the inside function with respect to n. The inside here, 1 minus lambda over n, can be rewritten as 1 minus lambda times n raised to negative 1. That's the inside. If I take derivative, 1 becomes 0. I bring negative 1 to the front. I get lambda times n raised to negative 2. That's the numerator. On the denominator, if I take derivative for 1 over n, 1 over n can be rewritten as n raised to negative 1. If I take derivative here, I bring negative 1 to the front. I get negative 1 times n raised to negative 2. That's the denominator. If I take derivative, I get negative 1 times n raised to negative 2. Then simplify. From the top and the bottom, I can first of all cancel n raised to negative 2. From the top and the bottom, I can first of all cancel n raised to negative 2. Then I can multiply lambda to the numerator here. I get limit as n approaches to infinity, lambda over 1 minus lambda over n divided by negative 1. I can bring negative 1 to the front. Then plug infinity. If I plug infinity, lambda over infinity is 0. I get 1 minus 0 on the bottom, which is 1. So that's negative lambda. That means as n approaches to infinity, Ln of y is negative lambda. As n approaches to infinity, Ln of y is negative lambda. So Ln of y is negative lambda as n approaches to infinity. If I solve an equation for y, I apply e to both sides. E of Ln of y equal to e raised to negative lambda. That means y equal to e raised to negative lambda as n approaches to infinity. So this expression is e raised to negative lambda. This expression, this limit, is e raised to negative lambda. So the second limit here is e raised to negative lambda. Now let's take the third limit. Limit n approaches to infinity. 1 minus lambda over n to the power of negative x. One minus lambda over n to the power of negative x. If I plug infinity for n, for lambda, if I plug in infinity for n, I get 1 minus 0 to the negative x, which is 1 raised to negative x. 1 raised to any power is 1. So the last limit is 1. Then together, f of x is e raised to negative lambda times lambda to the power of x over x factorial. F of x is the probability function of a random variable x. Here, in a fixed time interval, suppose lambda is the average number of the occurrence of the events. Suppose lambda is known. Then the random variable x represents the actual number of the occurrence of the events. Then we say x has a Poisson distribution with parameter lambda, and its probability function is f of x equal to e raised to negative lambda times lambda to the power of x over x factorial. The notation for Poisson distribution is x has a Poisson distribution or we say x is a Poisson random variable with parameter lambda. Its probability function is e raised to negative lambda times lambda to the power of x over x factorial. What's the support of x? What's the support of x? Here, x represents the actual number of the occurrence of events. So x could be 0, could be 1, could be 2, 3, 4, 5, until infinity. X could be all integers from 0 to infinity. So x could be all integers from 0 to infinity. That's the support of x. Also, in the probability function f of x, lambda represents the average number of the occurrence of the events. So in the probability function, lambda represents the average number of the occurrence of the events. In a fixed time interval, or place. And x, in the probability function x, represents the actual number of the occurrence of the event. In the same time interval or place. In the same time interval or place. In the probability function f of x, lambda represents the average number of the occurrence of the events, and x represents the actual number of the occurrence of the events. Next, let's look at some examples about Poisson distribution. Let x be a Poisson random variable with lambda equal to 5. For Poisson distribution, the number in the parentheses is always a perimeter lambda. In this case, lambda is 5. Find each of the following probabilities. Part A, probability that x equal to 4. Part B, probability that x equal to 7. Part C, probability that x is less than 4. Part D, probability that x is greater than or equal to 2. In order to find these probabilities, let's first of all find the probability function of x and the support of x. Since x has a Poisson distribution, its probability function is e raised to negative lambda times lambda to the power of x over x factorial. And here lambda is 5, so I plug in 5 for each lambda. I get e raised to negative 5 times 5 to the power of x over x factorial. That's the probability function of x. And the support of x. Since x is a Poisson random variable, support of x is the set of all integers from 0 to infinity. The set of all whole numbers from 0 to infinity. That's the support of x. Then, based on this, answer the questions. Part A. What's the probability that x equal to 4? Probability that x equal to 4 is f of 4. That means I plug in 4 into the probability function for each x. That's e raised to negative 5 times 5 to the power of 4 over 4 factorial. Then use calculator. I get 0.1755. That's part A. Probability that x equal to 4. Part B. What's the probability that x equal to 7? Probability that x equal to 7. That's f of 7. Which which means I plug in 7 into the probability function for each x. If I plug in 7, I have e raised to negative 5 times 7 to the power of x times 5 to the power of 7 over 7 factorial. Plug in 7 for each x. Then its calculator. Here I get 0.1044. That's the probability that s equal to 7. Part C. What's the probability that x is less than 4? If x is less than 4, look at the support here. X could be 0, 1, 2, 3. If x is less than 4, x could be 0, 1, 2, 3. So that's f of 0 plus f of 1 plus f of 2 plus f of 3. For f of 0, I plug in 0 for each x. I get e raised to negative 5 times 5 to the power of 0 over 0 factorial. For f of 1, I plug in 1 for each x. I get e raised to negative 5 times 5 to the power of 1 over 1 factorial. For f of 2, I plug in 2 for each x. I get e raised to negative 5 times 5 to the power of 2 over 2 factorial. For f of 3, I plug in 3 for each x. I get e raised to negative 5 times 5 to the power of 3 over 3 factorial. Then use calculator. Here I get 0.2650. If I round the answer to 4 decimal places, I get 0.2650 in my calculator. Part D. Find the probability that x is greater than or equal to 2. Look at the support here. Support is a set of all integers from 0 to infinity. For probability that s is greater or equal to 2, s could be 2, 3, 4, 5 until infinity. There are too many terms. If we try to solve it directly, it may be too complicated. So let's think of the complement. If x is greater or equal to 2, the opposite is x less than 2. If x is less than 2, s could be either 0 or 1. That's much easier. So probability that x is greater or equal to 2, if I use complement, it can be rewritten as 1 minus probability that x is less than 2. Look at support. If s is less than 2, it must be 0 or 1. So that's 1 minus f of 0 plus f of 1. F of 0, we plug in 0 for each x. That's e raised to negative 5 times 5 to the power of 0 over 0 factorial plus e raised to negative 5. If I plug in 1 for x, I get 5 to the power 1 over 1 factorial. So in this formula, plug in 0 and 1. Then here I use my calculator. Use my calculator, round to 4 decimal places. I get 0.9596. That's the probability that x is greater than or equal to 2. Next example, John is a salesman in a store. Based on a past experience, he can sell TVs at an average rate of 6 TVs each day. Part A, in a given day, what's the probability that John sells exactly 5 TVs? Part B, in a given day, what's the probability that John couldn't sell any TVs? Part C, in a given day, what's the probability that John sells at least 2 TVs? In this problem, we know that John can sell TVs at an average rate of 6 TVs each day. If we consider selling a TV is an event, then we know that the event occurs 6 times a day on average. If we know the average number of occurrences of the event in a fixed time period, we can consider using Poisson distribution. So let's set down the problem first. Let the random variable x represent the number of TVs sold by John. In a day. Then, what do we know here? Since we know average number of selling TV, average number of TV sold by John on each day, X is a Poisson distribution. On average, John can sell 6 TVs each day, so lambda is 6. On average, John can sell 6 TVs each day. Next, let's write down the probability function. Probability function for Poisson distribution is e raised to negative lambda times lambda to the power of x over x factorial. Here, lambda is 6. We plug in 6. We get e raised to negative 6 times 6 to the power of x over x factorial. That's the probability function of x. Next, let's find support of x. Since x has a Poisson distribution, its support is the set of all integers from 0 to infinity. The set of all integers from 0 to infinity. Now, based on the setup here, answer the question. Part A. In a given day, what's the probability that John sells exactly 5 TVs? So in part A, we are looking for probability that S equal to 5. In a given day, John sells exactly 5 TVs. Probability that S equal to 5 is f of 5. That means we plug in 5 for each x. Plug in 5 into the probability function for each x, which is e raised to negative 6 times 6 to the power of 5 over 5 factorial. And then here I use my calculator, I get 0.1606. That's part A, the probability that John sells exactly 5 TVs in a given day. Part B, in a given day, what's the probability that John couldn't sell any TVs? So for part B, we're looking for probability that S equal to 0. The number of TVs sold by John is 0. What's the probability that John couldn't sell any TV? It's probability that S equal to 0. Probability that S equal to 0, that's f of 0. For f of 0, we plug in 0 for each x. We have e raised to negative 6 times 6 to the power of 0 over 0 factorial. 6 to the power of 0 is 1. 0 factorial is also 1, which is e raised to negative 6. And then here I use my calculator. E raised to negative 6 is 0.0025. I round the answer to 4 decimal places. I get 0.0025. Part C. In a given day, what's the probability that John sells at least 2 TVs? At least 2 TVs means 2, 3, 4, 5 or more. So part C, we're looking for probability that x is greater or equal to 2. John sells at least 2 TVs. If we look at support here, at least 2 means number x from 2, 3, 4, 5 until infinity. There are too many terms here. So let's think of the complement. If we solve it directly, it may be too complicated. Let's think of the complement. Greater or equal to 2, opposite is less than 2. If s is less than 2, we have only 0 and 1 in the support. So think of the complement, it will be much easier. Probability that s is greater or equal to 2, the complement is 1 minus probability that x is less than 2. If s is less than 2, s can only be 0 or 1. So that's probability that that's 1 minus probability that s is less than 2. If s is less than 2, s must be either 0 or 1. For f of 0, we plug in 0 for each x. That's e raised to negative 6 times 6 to the power 0 over 0 factorial. For f of 1, we plug in 1 for each x. That's e raised to negative 6 times 6 to the power 1 over 1 factorial. That's 1 minus e to the power of negative 6. 6 to the power 0 is 1. 0 factorial is also 1. E to the 6 times 6 to the power 1 is 6. 1 factorial is 1. That's 1 minus 7 times e to the negative 6. Then use my calculator here. I use my calculator. Round the answer to 4 decimal places. I get 0.9826. That's the probability that s is greater or equal to 2. Next example, vehicles visit a gas station at an average rate of 30 vehicles per hour. Part A, what's the probability that no vehicles visit a gas station in a given minute? In this problem, we know that vehicles visit a gas station at an average rate of 30 vehicles per hour. If we consider the event that a vehicle visits a gas station, then based on the problem, this event occurs 30 times per hour on average. If we know the average number of occurrences of the event in a fixed time period, we can use Poisson distribution. In part A, we're looking for the probability that no vehicles visit a gas station in a given minute. If we know the average number of occurrences of an event in a fixed time period, and we are looking for the actual number of occurrences of an event in a given time period, we can use Poisson distribution. So let the random variable x represent the average number of visiting vehicles in a given minute. Then x has a Poisson distribution. For Poisson distribution, the perimeter is lambda. What's lambda here? Lambda represents the actual number of occurrences of an event in a given time period. Lambda represents the actual number of an occurrence of an event in a given time period. We know that the event occurs 30 times in 60 minutes. There are 30 vehicles per hour. There are 30 visiting vehicles per hour. Then on average, how many visiting vehicles in 1 minute? On average, how many visiting vehicles in 1 minute? We can use proportion here. Solve for lambda. 60, if I cross multiply, I get 60 lambda equal to 30. Then divide both sides by 60, lambda equal to half. This number means, on average, there are half visiting vehicles in a minute. On average, there are half visiting vehicles in 1 minute. Then x has a Poisson distribution with lambda equal to half. On average, there are half visiting vehicles in 1 minute. Next, let's write down the probability function of x. For Poisson distribution, probability function is e raised to negative lambda times lambda to the power of x over s factorial. Then plug in lambda here. Lambda is half. I get e raised to negative half times half to the power of x over x factorial. Next, let's find support of x. Since x has a Poisson distribution, support of x is the set of all integers from 0 to infinity. In part A, we're looking for the probability that no vehicles visit a gas station in a given minute. So in part A, we're looking for the probability that s equal to 0. The number of visiting vehicles equal to 0. That's f of 0, which means I plug in 0 for each x. Plug 0 into the probability function for each x. I get e raised to negative half times half raised to power 0 over 0 factorial. We know that half raised to power 0 is 1. 0 factorial is also 1. So what's left is e raised to negative half. Then use calculator, round the answer to 4 decimal places. Here I get 0.6065. That's the probability that no vehicles visit a gas station in a given minute. That's part A. Part B. What's the probability that exactly 2 vehicles visit a gas station in a given 3 minutes? In general, if we know the average number of the occurrence of an event in a fixed time period, and we are looking for the actual number of the occurrence of an event in a given time period, we can use Poisson distribution. So here, let the random variable x represent the number of visiting vehicles . in a given 3 minutes. Then we know that x has a Poisson distribution. For Poisson distribution, the perimeter is lambda. Let's find lambda first. Lambda represents the average number of the occurrence of an event in a given time period. Lambda represents the average number of the occurrence of an event in a given time period. We know that on average there are 30 visiting vehicles every hour, and we are looking for how many visiting vehicles in 3 minutes. We're looking for the number of visiting vehicles in 3 minutes. Then we can use this proportion to solve for lambda. If I cross multiply, I get 60 lambda equal to 90, and then solve for lambda. Lambda is 3/2. That means on average there are 1.5 visiting vehicles in 3 minutes. On average there are 1.5 visiting vehicles in 3 minutes. 3/2 is 1.5. On average there are 1.5 visiting vehicles in 3 minutes. Then here x has a Poisson distribution with lambda equal to 3/2. Next, let's write down its probability function. For Poisson distribution, the probability function is always e raised to negative lambda, lambda to the power x over s factorial. Here, plug in lambda, I get e raised to negative 3/2 times 3/2 to the power of x over s factorial. That's the probability function of x. Next, let's find the support of x. For Poisson distribution, support of x is always in the set of integers from 0 to infinity. Support of x is always in the set of integers from 0 to infinity. Now, in part B, we're looking for the probability that exactly 2 vehicles visit a gas station in a given 3 minutes. So in part B, we're looking for the probability that x equal to 2. Probability that x equal to 2 is f of 2. For f of 2, we plug in 2 for each x in the probability function. Plug in 2 for each x. I get e raised to negative 3/2 times 3/2 to the power of 2 over 2 factorial. And then use calculator. Round the answer to 4 decimal places. I get 0.25 and 10. 2510. I get 0.2510. That's the probability that exactly 2 vehicles visit a gas station in a given 3 minutes. Part C. What's the probability that at least 2 vehicles visit a gas station in a given 5 minutes? In general, if we know the average number of the occurrence of an event in a fixed time interval, and we are looking for the actual number of the occurrence of an event in a given time interval, we can use Poisson distribution. So here, then the random variable x represents the number of visiting vehicles in a given 5 minutes. Then x has a Poisson distribution. For Poisson distribution, the perimeter is lambda. Let's find lambda first. In general, lambda represents the actual number of the occurrence of an event in the given time period. So here, lambda represents the actual number of visiting vehicles in 5 minutes. We know that on average, there are 30 visiting vehicles in 60 minutes. Then, how many vehicles in 5 minutes? Let's use this proportion here to solve for lambda. If I cross multiply, I get 60 lambda equal to 150. If I divide both sides by 60, I get lambda equal to 5/2, which is 2.5. That means on average, there are 2.5 visiting vehicles in 5 minutes. On average, there are 2.5 visiting vehicles in 5 minutes. So X has a Poisson distribution with lambda equal to 5/2. Next, let's find the probability function. For Poisson distribution, the probability function is always e raised to negative lambda times lambda to the power of x over x factorial. Then we plug in lambda. I get e raised to negative 5/2 times 5/2 to the power of x over x factorial. That's the probability function of x. Next, let's find support of x. For Poisson distribution, support of x is always the set of integers from 0 to infinity. The set of integers from 0 to infinity. In this problem, we're looking for a probability that at least 2 vehicles visit the gas station in a given 5 minutes. At least 2 means 2 or more. So we're looking for a probability that x is greater or equal to 2. Number of visiting vehicles is greater or equal to 2. Here, support of x is from 0 to infinity. If x is greater or equal to 2, then x could be 2, 3, 4, 5 until infinity. There are too many terms. So let's think of the complement. The complement of x greater or equal to 2 is probability that x less than 2. The complement of probability that x is greater or equal to 2 is probability that x is less than 2. Here, support is from 0 to infinity. If x is less than 2, then x could be either 0 or 1. If x is less than 2, x could be either 0 or 1. So that's 1 minus probability that x is 0 plus probability that x is 1. When x is less than 2, x could be either 0 or 1. So I plug in 0 to the function for x, and then plug in 1 to the function for x. I get e raised to negative 5/2 times 5/2 to the power of 0 over 0 factorial plus e raised to negative 5/2 times 5/2 to the power of 1 over 1 factorial. Then use calculator. Round the answer to 4 decimal places. Here I get 0.7127. That's the probability that at least 2 vehicles visit a gas station in a given 5 minutes. That's an answer to part C. Next example. In a factory, the probability of producing a defective toy is 0.002. In a box of 3,000 toys, what's the probability that exactly 4 toys are defective? In this problem, we know that for each toy, the chance of being defective is 0.002, and there are 3,000 toys. If we know the total number of trials, and for each trial, the chance of getting success is the same, we can use binomial distribution. So, the random variable x represents the number of defective toys in the box. Then x has a binomial distribution. With n equal to 3,000. And p equal to 0.002. There are 3,000 trials, and for each trial, the chance of being success is 0.002. We consider getting a defective toy represents success. So for each trial, the chance of being success is 0.002. X has a binomial distribution. The probability function is n choose x times p to the power of x times 1 minus p to the power of m minus x. then plug in n and p. If I plug in n, I get 3000 here. 3000 choose x. P is 0.002 to the power of x. 1 minus p is 0.998 to the power of m minus x. Here n is 3000. Next, let's find support of x. X has a binomial distribution. For binomial distribution, support of x is the self-integers. The self-integers from 0 to n. The self-integers from 0 to n. 0, 1, 2 until n. Here n is 3000. That's support of x. What we are looking for is a probability that exactly 4 toys are defective. So we're looking for a probability that the number of defective toys is 4. We're looking for probability that the number of defective toys is 4. Then we plug in 4 for x in the probability function. Here I get 3000 choose 4. 0.002 to the power of 4. 0.998 to the power of 3000 minus 4 is 0.2996. Here I use my calculator. In my calculator I get 0.1338525132. That's the probability that exactly 4 toys are defective. Now, for this problem, if we solve this in the calculator, this calculation may be too complicated. Can we solve this problem in a different way? Note, for any binomial random variable, when n is large, p is small, and n times p is less than 10, we can use the Poisson random variable to approximate the binomial random variable with lambda equal to n times p. In the beginning of the class, we know that when n is large, p tends to lambda over n. When n is large, p tends to lambda over n. If I try to solve this equation for lambda, I can multiply both sides by n. I get lambda equal to np. So when n is large, p is small, and n times p is less than 10. We can use a Poisson random variable to approximate a binomial random variable with lambda equal to np. Now, in the previous example, in example 4, n is 3000. N is 3000, which is considered large. P is 0.002, which is considered small. And n times p, 3000 times 0.002 is 6, which is less than 10. So in example 4, I can use a Poisson distribution to approximate the binomial distribution. So we can use the Poisson distribution to approximate the binomial distribution. Here we can use a Poisson random variable to approximate the binomial random variable. The binomial random variable x. Here we can use a Poisson random variable to approximate the binomial random variable x. In example 4, we know that x has a binomial distribution with n equal to 3000, p equal to 0.002, if I use Poisson random variable to approximate this binomial random variable, lambda equal to n times p. Here, n times p is 6. In example 4, n times p is 6. Lambda equal to 6. What does this number mean? This number, lambda equal to 6, that means on average, in a box of 3,000 toys, on average, we expect to have 6 defective toys. On average, in a box of 3,000 toys, we expect to have 6 defective toys. That's what 6 means. What we are looking for is the probability that there are exactly 4 defective toys in the box. There are exactly 4 defective toys in the box. So we are looking for probability that s equal to 4. We should run a probability function first. For Poisson distribution, the probability function is e raised to negative lambda times lambda to the power of x over x factorial. Plug in lambda, I get e raised to negative 6 times 6 to the power of x over s factorial. Support of x. For Poisson distribution, support of x is the self integers from 0 to infinity. For Poisson distribution, support of x is the self integers from 0 to infinity. So for probability that x equal to 4, I'm looking for f of 4, which means I plug in 4 into the probability function for each x. That's e raised to negative 6 times 6 to the power of 4 over 4 factorial. Then here I use my calculator. I get 0.1338 526 175. That's what I get in my calculator. If we compare this answer with the previous answer, this is the actual answer. This is the actual answer. This is the approximate answer using Poisson distribution. Here we can see that they are very, very close. 1, 2, 3, 4, 5, 6. The first 6 digits are exactly the same. 1, 2, 3, 4, 5, 6. The first 6 digits are exactly the same. So they are very, very close to each other. That's a good approximation. But this computation here looks much better than this. So in general, for any binomial distribution, if n is large, p is small, and n times p is less than 10, we can always use the Poisson distribution to approximate the binomial distribution with lambda equal to m times p. In general, the computation in Poisson distribution is easier than the computation in binomial distribution. Their answers are very, very close, but the computation in Poisson distribution is much, much easier.